Good morning, my name is Gary Swinkels, and I'm going to talk to you about hyperscale routing and what the GCNs are doing inside the data center. There's a number of things that the hyperscalers are asking equipment providers to do for them to make their networks more efficient. And I want to talk to you about what they're doing and where they're planning to go. So the requirements are very simple. Unlike a regular router, the hyperscalers want full access to everything inside their router. They want to be able to program and set routes with fine control, get fine feedback. And I think you've seen this theme throughout the various presentations, is there's a desire for more control. You can do it many, many ways. The other challenge that they have is in one of scale, and this is particularly difficult to build. Is a very large scale router. So is it 4,000 ports you want? Is it 20,000 ports you want? Is it 100,000 ports you want? So the general ask is in that 100,000 port range, and what can you do for me? So let's go see. Today, if we go onto the market and we look for routers come in a few varieties, and I think we recognize these. We've got the pizza box sizes with a sub 100 port count. You've got some shelf-based routers that are as tall as I am, no problem. And then you've got some disaggregated routers that are now coming onto the market, and they get into the 4,000 to 8,000 port range, depending on how you slice and dice it. So I mean, this is all stuff we know. We also know how to build a leaf spine, and this is what you see classically being practiced in the front-end network of a data center. They don't have a 4,000 port router, they don't have a 100,000 port router, so they're going to deploy routers and make a spine leaf architecture, or a leaf spine architecture, and then they're going to connect their clients into it. This architecture works okay. There's a lot of moving parts. Oops, did I jump ahead? There's a lot of moving parts to make it happen. The real challenge comes into knowing that the connectivity is correct, that the links are up and operational, where is the congestion, and all of these nodes you need to be mining data, either with SFlow, IPFix, all sorts of metrics, so that you can understand where the hotspots are and alleviate them before they take out the traffic. So this is practiced in both the front end and the back end part of the network. The front end is where we typically set up the servers. The back end is where I'm going to talk about next, which is with the GPU connectivity, which is really the challenge that I think that a number of presenters have highlighted. The one thing I will point out is that the GPUs that are currently being built yesterday, today, and tomorrow aren't at the same port size. So you can buy a GPU or a server with 100 gig NICs, but your router port may have a 400 or 800 gig NIC. And so it's possible to channelize these interfaces and hook up a lot more servers or GPUs onto your quote router, whether it's a leaf spine or a monolithic router. And this is something that when people come in and ask for scale numbers, if you just say, oh, port to port, some people forget to ask the question, what is the size of the port? And so we've had a few miscommunications, shall we say, in terms of the number of GPUs you want versus the number of router ports that are actually needed. So what does the back end look like? So there's a different terminology being used in the back end. When you buy a cluster of GPUs, I don't know if you've purchased these, but you're into per rack somewhere between $1.5 to $3 million worth of GPUs and a little bit of networking gear. And we call that the scale up part of the network. And in that rack, you'll have a variety of servers hosting GPUs. You'll have some sort of a switching fabric, sometimes InfiniBand, sometimes Ethernet, and basically providing full connectivity between all the GPUs within that rack. Very non-blocking, very low latency, works really well, but it doesn't get you into a high number of GPUs. It's just a few GPUs in the rack. I will say that when you air cool, you get one number, and when you liquid cool, you can kind of double that number, which is sort of an interesting thing. And when you look at the liquid cooling initiatives being done in the data center, that's why they're doing it. It's all about getting the saving energy from cooling and getting more GPUs in the rack than you actually, more GPUs. And it's all about space and power at the end of the day. What else did I want to highlight on this? In this network, so in the scale-up domain, you have, it works very, very well. It's rather efficient. But for some of the workloads, some of the large language model, the training models that are being deployed, it's just not enough. You don't need less than 100, you need 1,000. And so you end up building this scale-out network. And basically, you're connecting these racks together. And you can imagine if you're trying to get to 100,000 GPUs, and nobody is at 100,000 GPUs, so don't think that I'm telling you a fib. Nobody's at 100,000 GPUs, but we are building these GPUs out. The workload that is deployed is a very intelligent. When a large language model is deployed, the workload is distributed across these GPUs. If you have functions that are going to be using a lot of any-to-any traffic, the workload, the orchestrator will distribute that or attempt to distribute that into a single rack and save the slower network connectivity between the racks using the scale-out network. The scale-out network tends to be a congestion point, and there's a lot of work being done there. In this diagram, I've said, a large spine router or a spine network. Typically, they are spine networks still today. There is a desire to get to larger routers, and we'll get to that a little bit further in the talk. The one thing that you've heard over and over and over again about AI workloads is that they're very sensitive to loss. And that is all the work that the hyperscalers are asking us to do, asking Ciena and other product router providers to do, is give me access so that I can control, see the hotspots, prevent the hotspots from happening. Yes, the workload orchestrator does a great job, but it isn't perfect. Another way to get to 100,000 GPUs is to not fully connect the whole network together. And I think that when I first saw this, it really, really bothered me. How can you go from a fully mesh-connected scale-out fabric to a one with 25% connectivity? And what you need to realize is that the workload orchestrator doesn't care how it gets there. The workload, not all GPUs need to talk to all GPUs. The GPUs of interest are generally in the 20, 30, 50 range, where they're doing some any-to-any or an all-reduce or whatever. Those collective communication libraries are well understood. We know where to put the traffic. We know where all the traffic's going. It's wickedly predictive. It's not like the network is designed to support this workload. It's not designed to support some arbitrary workload that you don't have control over. And I think that's why this trading off full mesh connectivity for more ports or more connectivity overall works. You can pipeline from one scale-up rack through one of the rails back down to another scale-up domain and back, and you just stitch up and down all day long. The fact that you don't have full connectivity really doesn't get in your way. The other thing to realize is that the workloads, you might have, let's say, 20,000 GPUs, but you might be using 2,000. You'll be running various jobs, and they don't care where they run, right? The workload orchestrator doesn't care. I, as a human, probably care. If I wanted to see what's going on, but the tooling behind how the large language model gets deployed, how the workload is put into the network, that's what saves us. If you had me do it, I'm sure I would do a very poor job. But the machine doesn't care, and that's what saves us in this space here. All right. We've heard this over and over again, that AI workloads are extremely sensitive to loss. There's a number of reactive protocols that we put into the network, PFC, ECN, there's a whole host of them. I'm not going to go through them. I could do a whole presentation on how you're going to do that. The challenge is we are looking to, when we see congestion, to avoid it. As we know, loss is also a problem. Discarding packets, you can actually wreck a whole training workload if you have a hiccup in your links. Where I want to go here. Oh yeah, so I wanted to also mention there's a consortium, the Ultra Ethernet Consortium, that's going to attack this problem, and I'm looking forward to seeing what they're doing. Not seeing a whole lot of them now, but you're going to hear me talk about them a little bit later in the presentation. We've talked about, or many people have talked about, ECMP doesn't work, so I'm not going to talk about ECMP doesn't work. I think that when we have congestion in the network, ECMP is our friend, but when we have elephant flows and you can't take them apart, ECMP is not our friend. And that's the message here. On the other end is traffic engineering. Traffic engineering is kind of the two bookends. The traffic engineering works surprisingly well, but it is not simple. You need a lot of information from your network. The advantage that the AI workloads have is, in addition to all of the link utilization metrics that you would typically see, is we're able to harvest chakra traces of what the AI system is doing, where it's at, how it's performing. And so we've got additional information. It gives a double advantage. We not only know what the traffic is, where it's going, and when it's going to be busy and not busy. And this allows us to actually do a lot more traffic engineering. We can push policy into the network and basically balance out the AI backend so that we can really avoid congestion. This works super well. It is not free. It is a lot of work, but it works very well. It actually, out of all the things that I've seen, all the tests from the various bits that we've done, it provides the best flow completion times. So that's excellent. So how about these high port count routers? I mean, we've been talking about the network and everything that's there. So what's the deal with these high port count routers? Why do I need to get to these things? Well, the nice thing is elephant flows. They don't have a problem with elephant flows. So we take the elephant flow, we take it apart, we pass it over the fabric and back out again, and we don't get any congestion. We get more ports. It works super well. In some cases, you don't even need additional queuing memory. It's depending on what you're doing. So some of the challenges that are coming down the pipe. So we've done a lot of work to actually look into the AI backend networks, looking at different protocols. Every week I read another paper about somebody's done experiments. Again, at the end of the day, it looks like traffic engineering always wins, but I'm sure somebody will crack that nut someday. The other thing that's concerning to me is inferencing and large language models are only getting bigger. I spend most of my time looking at large language models. However, inferencing is beginning to pop up. And that's, it's gone from a few GPUs to tens of GPUs now. So it's actually moving up, and I think that people want more value out of when they're working with the inferencing engine, so great, let's give them that. The last one I have is, could something in the future, could we make changes to the collective communication libraries? Could we fix RDMA? There's been a tremendous amount of work done with the network interface cards to make RDMA more effective, but it's still those elephant flows we can't take apart. Is there something we should be looking at there? The UEC, Ciena is a member of the UEC. I'm sure that many people are. It promises to fix all these problems. I really think there's something here. It's just not on the immediate horizon, but it is coming and worth watching. So my last thoughts are, there is a reason that we're being asked to build these high port count routers. They solve a lot of the back-end problems. But if you don't have one of those, centralized TE is still the way to go. And that's it. Thank you.